Hi, thanks for joining me today. I've got a problem from the 1999 Polish Olympiad. We have a sequence of integers an which satisfies the rule an plus 1 equals an cubed plus 1999 for all positive integers n. We want to prove that there exists at most one value n for which an is a perfect square. So in other words, there's at most one square number in this sequence. Okay, so let's dive into a solution. The trick to this is to consider these numbers, or in particular square numbers, mod 8. So the first thing we'll do is make an observation. Firstly, if you take any integer, you can always write it in this form, 4n plus r, where r is a number between this, or in this set here, 0, 1, 2, or 3. So in other words, take any integer, you can divide it by 4, and then you'll get a remainder 0, 1, 2, or 3. And now what we're going to do is look at what we get when we square this. So 4n plus r squared is 16n squared plus 8nr plus r squared. And if we look at this mod 8, this is just going to be r squared, because this guy and this guy are clearly multiples of 8. Now, what could r squared be mod 8? Well, let's have a look. Well, if r is 0, this is just going to be 0. If r is 1, 1 squared is just 1. If r is 2, 2 squared is 4. And if r is 3, 3 squared is 9, but 9 is already the same as 1, so we've already got that in our list. So in other words, any square number is either 0, 1, or 4 mod 8. Cool. How do we use this observation? Well, what we're going to do is suppose that there is a square number in our sequence, and then we'll show that every single term after that cannot be a square. So, suppose an is a square number. So an is k squared for some integer k. Now, what we're going to do is do case 1, where k squared is in either 0 or 4, mod 8. Because obviously we know it's got to be one of these three numbers, so case 1 is going to be if k squared is 0 or 4 mod 8. What happens here? Well, if this is the case, let's just look at an plus 1, which remember is an cubed, so k squared cubed, so k to the 6 plus 1999. And if k squared is 0 or 4 mod 8, hopefully it's pretty clear that k to the 6 is going to be either 0 cubed or 4 cubed mod 8. Either way, it's going to be 0 mod 8, so this is going to be the same as 0 plus 1999, which is the same as minus 1 mod 8. Okay, cool. So that definitely can't be a square number because minus 1 is not 0, 1, or 4. Okay, what about an plus 2? Could that be a square? Well, again, we're going to look at this mod 8. And so we know it's going to be an plus 1 cubed, which we know is minus 1 cubed plus 1999. Again, this is all mod 8. And so this is going to be minus 1, which is minus 2 mod 8. Which again is not 0, 1, or 4, so an plus 2 can't be square either. Now, what do we get if we look at an plus 3? Well, we're going to get minus 2 cubed plus 1999. But minus 2 cubed is minus 8, which is 0 mod 8. And so we're just going to get minus 1 mod 8. And we get back here. And what you'll see is if you look at all the terms thereafter, it's just going to be the sequence minus 1, minus 2, minus 1, minus 2, and so on, mod 8. And therefore, it cannot be one of these three numbers, and therefore cannot be a square number. Amazing, so that's case 1 dealt with, if k squared is either 0 or 4 mod 8. Next, we just need to consider what happens if k squared is 1 mod 8. Okay, so k squared we're assuming is now 1 mod 8. Let's look at an plus 1. Well, an plus 1 is going to be an cubed plus 1999, and mod 8, that's going to be 1 cubed, which is 1, plus 1999, which is congruent to 0, mod 8. And so this could potentially be a square, because remember, square numbers mod 8 are 0, 1, or 4. Okay, cool. Let's look at an plus 2. What's that? Well, that's going to be an cubed plus 1999, which is 0 cubed plus 1999, which is congruent to minus 1, mod 8. And so we get minus 1, which we know isn't a square. And we can hopefully see that then an plus 3 would be minus 2, minus 1, minus 2, minus 1, minus 2, and so on. We keep getting the sequence that we got before. So the only potential way we could potentially get another square is if this guy here is square. So we've got to examine this case in a little bit more detail. So we're assuming that an is k squared, and let's assume for contradiction that this guy an plus 1 is also a square number. So an is k squared, and an plus 1 is, let's say, some number y squared. Well, what is an plus 1? Well, it's an cubed plus 1999, which would be k squared cubed plus 1999. And so now if we bring this to the left side, we get y plus k cubed, and then y minus k cubed equals 1999. Just kind of doing the difference of two squares here. Okay, now what's the issue with this? Well, we're going to now use the fact that 1999 is prime. Now, this isn't super obvious, but to be honest, if you're entering this Olympiad, you probably, a general number theory trick is to look up the prime factors of the year of the paper ahead of time, because kind of a customary thing in maths is if you have a number theory problem that involves kind of a fixed number, you try and make it that year, and it's all the better if that year is prime. But yeah, it does turn out that 1999 is prime. And so since these both are positive integers, one has to be 1 and the other one has to be 1999. And since that guy is clearly smaller, that would be 1 and that would be 1999. But the issue with this is then if I subtract these two from one another and divide by 2, I'd eliminate the y's and just get k cubed is 1999 minus 1 over 2, which is 999. But the issue is 999 is not a cube number. And so therefore it's impossible for this to be true. And so therefore this guy here cannot be a square. And we've proved case 2 is impossible. We earlier showed that case 1 is impossible. Hence, it is impossible to get another square. So in this list here, we have at most one perfect square. I hope this solution has made sense. It's a pretty cool way to use modular arithmetic to prove that something doesn't exist. If you are new to the channel, please do give this video a like and subscribe if you haven't already. Thanks for watching. I'll catch you in the next one. Have a great day.